Hello community. It is late in the night, but I just discovered tiny language model. They are beautiful for new pre-training methodologies. If you want, we have a look together at BERT architecture, at the Llama architecture, and at S&M and Mamba architecture, and we will focus on tiny language models. And at the first, I thought, hey, I work with DeepSeek version 3. And I love this model, but it has close to 700 billion free trainable parameters, and I have no hardware architecture that I can experiment with the architecture itself. So therefore, we look now at models that are really tiny. And I mean tiny models. Compared to this is a 14 million model. So however, the size, I think it's a hot topic in AI. And you know why? Because the model size is a neglectable 0.002% of a DeepSeek version 3. But this is where we can experiment. This is where we can find out the learning mechanisms and we can optimize here our training methodologies. I have no way of finding out new ways for optimizing the training on a 700 billion free trainable parameter LLM. But you know what? If you think about edge devices, and if you think that in some years, maybe quite a lot of those little devices will have a rudimentary AI intelligence. So why not think today already here on training here tiny little LLMs that still exhibit some robust linguistic understanding and some reasoning abilities. And they are the perfect size and the perfect object to further experiment with optimization. There's now a new research paper I would like to show you, and they explore here creating simplified language environment to train particular those tiny language models. And their idea is here simple, yeah? Like children that learn a language, basic vocabulary, a simple syntax at the first words, at the first sentences. And those tiny LLMs, let's have a look if we can implement somehow this idea, this simplicity or simplified language environments also with them. Now it's interesting that the scaling down, this is a very sensitive topic. So to achieve here the simpler environments, the authors I'll show you in a minute, they created here a leaner dataset. So by revising existing test datasets to reduce the noise and limit the vocabulary size, we will work here with a vocabulary size of down to 2000. And our main task, we will have to simplify complex ideas. Because we are working with models that are so tiny, it's no way that they have some complex ideas that they can calculate. So I will show you then the prompt at the end of this video, how we do exactly here the downscaling, the simplification of complex ideas. But for the moment, let's focus on the methodology itself. For the data, it is relatively easy, and I'll show you the prompt that we have a DeepSeek, for example, to revise the dataset and create those simpler dataset. And of course, we can make it much more interesting if we have now this open architecture by integrating now what is called a curriculum learning. Very simple idea. The model is first trained on some simple, non-complex data, and then we gradually expose the model in the training phase, especially in the pre-training phase, to more complex data, to a higher complexity in the reasoning structure of our informations. And then, of course, we can focus now on training these tiny LLMs, and we implement now instruction following procedures. And this is what we need to build autonomous agent. And as I told you, those edge devices, and you see there's somebody missing here. If we succeed to have tiny models here, almost in every gadget that is out there, we have to make sure that this intelligence is reliable, that it is performant. So building here autonomous agent, this is a real challenge to make them simple, high performant, cheap to implement, simple to maintain, and to coordinate here in a swarm. So we also will go to the step where we say, okay, we will focus now to build self-evolving engines, because nothing worse than an agent that has no real possibility to advance itself, to learn new stuff. So self-evolving agents that are based on tiny LLMs, This is an absolute fascinating topic, and up until now I ignored tiny LLMs on my channel, and I would like to correct this. Now, you might say, and I thought the same, that, okay, we just use a huge AI system, O1 or O3, to train now our tiny LLMs. And we have, given history, a lot of methodologies: knowledge distillation, model compression, teacher-student learning, model transfer. A real nice one is the supervised fine-tuning with LLM supervision, or you just go with a proxy model training procedure. But interestingly, reading now these new papers, I thought this is not the way forward, However, interestingly, there was an author that said, hey, training the tiny LLMs now on our leaner data set with a reduced complexity will enhance now the learning efficiency and allow our tiny LLMs to perform better on downstream tasks. So those tiny LLMs are now trained on leaner data set, and the hope is that they can achieve similar or even have better performance for specific tasks that are for those edge devices designed, compared if you would put there a complex LLM with an internet connection to your server in China or in Silicon Valley or wherever your model is positioned. So let's explore this and let's see where the research is today. We are now entering here how to compose those training dataset and pre-training dataset for tiny LLMs. It is not simple at all, especially if we allow the agent or the model, the tiny LLM, in their training strategy to actively seek knowledge during the pre-training phase. So this is a new form of pre-training, and this video now is a continuation of my video from yesterday, where we were talking about new pre-training methodologies for normal LLMs. But if we simplify to the max, there are some new insight I found fascinating. Yeah, and models pre-trained on easier data with a lower complexity, and we will connect here the information density, the complexity, and the information entropy in about 5 minutes. The idea is to improve the ability of those tiny LLMs to follow instruction. But this is a really delicate, sensible equilibrium that we have to take care of. Now, you can imagine if we work with those tiny LLMs, there's a trade-off. A trade-off between reducing the complexity of our training dataset and what the tiny LLM is able to perform in a downstream task, and retaining here the model's ability to perform well on unseen data, to generalize with unseen data. So there's this balance here of kind of simplifying the dataset down to a certain limit. Maybe we use the entropy equation to find out where is the threshold. And the other side of the limit is, of course, that we need here a rich distribution of the data. So the LLM, the tiny LLM, is not simply just memorizing the training data, and we have an overfitting. So the goal is now, by keeping the structure of this pre-training dataset aligned with kind of the conventional LLM that we know, and also simplify the data for an easier learning, the authors aim to increase now this general tasks ability of tiny LLMs. This is the paper we're going to talk about. You see, the very last day of December 2024, we have here those researchers from the University of Illinois, and they have an interesting title: Training and Evaluating Tiny Language Model in a Simpler Language Environment. And maybe if you just read the title, I was not aware about the impact this idea could have. You have here the GitHub, you have the code, you have the data set, you can go and you can experience this yourself. But I would like to focus here on the idea. So the idea is to create such a simple language environment. The authors here said, we want to build here a minimizing language dataset noise and a minimum complexity in our dataset in order to preserve here the essential characteristics of the text distribution. As I told you, we want to have a variety of different data distribution from different domains, so that the model is able, although it's highly specialized, to perform here maybe even a more complex reasoning. Let me give you here some simple insight here from this publication. So this is the publication, and now we jump into the publication, the dataset. For a normal LLM, for a multi-700B model, This would be a sentence that the model is able, because it has been trained, I don't know on how many trillion training tokens. But if we go down to the tiny LLMs, we have now to make things, even from the semantic content, simpler. So this is now where our new training process, this is the result. So we simplify this sentence to this sentence. Let me give you another example. Entrepreneurship, business management. This is here a normal, complex sentence, but we have to simplify it for our tiny LLM. And this is now the simplified case that a tiny LLM can beautifully run and understand. So what we did, we reduced the semantic complexity of our sentence. We reduced here the amount of vocabulary that we use down to 2,000 tokens. And we want to find out, with this minimum configuration, better new training procedures. And where are some thresholds and what we have to take care of. And this is now able, we can do it. We can run our experiments because it is not a 685 billion free trainable parameter model somewhere positioned in China. I was talking here about trying to find those thresholds. And yeah, we can work with information entropy, and it is a beautiful idea. But I just want to focus here on the grander scheme, what we're talking about. I would like to draw your attention to this publication here, a survey on self-evolution of large language model. Highly interesting paper. You have the GitHub and everything available here. Yeah, I was asked, do I have to really read all those papers? No. If you are interested, if you want further details, then I give you this paper because I've read them, I found it interesting, I found them helpful for me. But it is not that you have to read those papers. I try to explain it in a way that you should be able to follow my crazy ideas. Yes, I know not a lot of other YouTubers do follow those rather abstraction and present you only single papers, but I like to go cross-discipline, and let's explore this. So what they do is here, they say, hey, the classical framework for developing your self-evolving agents in AI. Typically, you have your 4 stages: the experience acquisition, the experience refinement, the updating, and the evaluation. Now, if we look here at our actual model here, they do it a little bit different, because they say here, as a complement to what is the classical procedure, we propose here the self-evolving agents from our tiny LLMs that are actively seeking new knowledge for the continual improvements. Now, this is interesting because if those tiny LLMs go out on the internet, they have now to convert a normal complexity semantic content down to their understanding. And this is already an adventure in itself, and we are not talking about optimization of training procedures, especially in the pre-training stage. If you think this is new, no. I learned and I was amazed that, look, there are other elements or other stories, Tiny Dialogue, Baby LLM, and Mini GPT 2023, 2024. You see minimal data sets and a model size from 1 million to, I don't know, 165 million. But today, we are focusing here on this model, on this paper that I showed you, because they call it TinyHelen, because they have now the insight from all the other models, and they try to build now the new best-in-class tiny LLM. So we look now at a 14 million free trainable parameter architecture of our deep neural network. And this is now connected, if you are looking a little bit into the semantic, into the linguistic structure, how we talk, how we have a complexity when we express ourselves. I found this study helpful here by Stanford University, a recursive deep model for semantic compositionality over a semantic tree bank, never mind. Stanford introduced here the recursive neural tensor network, and I think this gives you here a good idea if you want to have in computer science an idea where we are with complexity assessment of human language and how we can maybe reduce the complexity but keep the semantic information. So this explores how to data simplification through filtering here web data truncations using here vocabulary of extreme 20,000 words can induce here emergent abilities in tiny models. this is a question in itself. Are there emergent abilities, especially in tiny models? I would put here a big question mark, but okay, if you want to go here with the research from Stanford, yeah, great paper to read if you are interested in this. At the beginning, I told you we are going to look at different architectures. Now, you are familiar with the transformer architecture, where we have either the BERT architecture or something like a llama architecture, autoregressive decoder, but there's also here the Mamba architecture. And if you're new to AI, I have here 2 videos where I explain, hey, Mamba AI S6 are better than a transformer, and I code here with you here a mixture of expert model here with a transformer, the code, and we also, if you go back to the pure Mamba, we fine-tune it, we have a DPO alignment, I show you here the code, we do a test assessment, and I even have a video if you want to go beyond the classical Mamba AI implementation. If we say, okay, we want to integrate now self-attention here, we can do this with vector fields. So you see, already 1 year ago, we went far beyond what is called Mamba today. Now let's look at the models that they looked at. The first is a simple BERT model. You remember the encoder part of the transformer, a 14 million model size, vocabulary size 2000. Then they go for the decoder for the llama, 14 million. You see, vocabulary size of 2000. So just to make this sure, this is a really experiment. This is really a simplified demonstration, but with the full computational complexity. And now the question is, are we able to scale from this 14 million tiny, almost nothing size to more potent edge devices or even to normal LLMs? So we are not looking up to huge models, but we are really looking down. How small can we go with the architecture that you have an AI on your Apple Watch that is really locally performing the intelligence? Yeah, and then the Mamba task here, this is the specification of the 14 million Mamba project. For the hardware, I think it's interesting what you have to use for a 14 million pre-training, and they used here 4 NVIDIA A6000 with each of 48 gigabyte. If you're interested in Mamba-based language model, I think this is here an excellent summary, a study by NVIDIA, University of Wisconsin, Princeton University, Together AI, Carnegie Mellon. They give you here really, I would say, state-of-the-art of selective state space model like Mamba. And you know, that was in the summer of 2024. It was almost famous because they showed here that pure SSM-based model match or even exceed sometimes here their transformer in many tasks, especially the Mamba and the Mamba 2 models lag behind the transformer model on specific tasks that require in-context learning. And now you see why all of my last 2-3 videos were also about in-context learning and understand with mathematical models like here the Dirichlet energy minimization, how the in-context learning works. Or the lag behind here the abilities if you have a transformer architecture for long context reasoning. Just as a summary, if you are not really familiar with this. Another document, and I have to give you here the precise reference because this is copyrighted by the Association of Computational Linguistics. It is an old document. It is from June 2024, but I think it's an excellent summary. This is here a pre-training guide to training here, the pre-training data for an LLM, data age, domain coverage, quality, toxicity. And the authors are MIT, Cornell University, Google Research, OpenAI, and Carnegie Mellon University. So they pulled together their findings and their ideas, and I think this is great. And the authors here of our main study that we examined today, they used this pre-training guide, especially for the pre-training data design. So all the insights that you might find here, that you say, I don't know where they got this idea, this would be your reference documentation. Great. Now, our authors had 3 main questions they were interested in. Can training now with some clean data sets that have this lower linguistic complexity, can they enhance here the learning efficiency of LLMs and then of tiny LLMs? And you would assume, yes, of course. Then, second question was, do the language models pre-trained and instruction-tuned with these low complexity data sets tend to develop here this instruction following abilities earlier? Are they maybe even better to be on the road to develop to autonomous self-learning AI agents? And the third question was, hey, would they enable here a more efficient development of our language model architecture and of the training techniques, especially if we have on edge devices a resource efficient, a reduced scale? In Annex B, they give you some interesting insights, and you can feel that they want to find a relationship between the complexity of the language dataset for the scaling intention and its data distribution properties on the different domains. So they say, hey, we define the complexity of a language dataset to be the total number of token combination patterns presented with the dataset. And they give you here a definition of a naive complexity, as they call it, in the training techniques. And of course, the context window length, the size here, affects here the complexity. And they analyze here, if you want, the complexity of the dataset and put it in relation here to the information entropy. Yeah, if you want to have here the notation for all the variables, this is the explanation you need. But let me translate this formula in simple words, since we are talking about tiny LLMs. So what do you have? They have the lower bound and the entropy. So the lower bound of this mathematical formulation with the exponential of information entropy implies that reducing the entropy of a dataset. This simply means by making here the word distribution more predictable. You remember the next token prediction, autoregressive, for making here a dataset simpler. It reduces its overall complexity and thus is easier for language models to learn from, especially the tiny language model. I would say this is nothing I would doubt. I would say, yeah, this is a given. And then they say for the upper bound and the dataset size, the upper bound with the exponential of the token and the log tokens shows that as the dataset size, this means the number of the tokens increase, so does the complexity. This is, yeah, it is self-explanatory, but I think there are a lot of hidden complexities, especially in their formulation. I think I understand why they do it here. And their goal is to provide here a formal mathematical measure for evaluating the dataset complexity for their scaling. But, I don't know. I have a feeling that their proof here, yes, it supports here, in their view, the data preprocessing approach to reduce the complexity by simplifying the language, thereby reducing the entropy of the information to train smaller models effectively. But this is nothing that I would doubt. This is what I would expect, I would be more interested here in the hidden complexity. That is not that you say, yeah, if you make the dataset simpler, you reduce the complexity, that therefore it is easier to learn. Yes. But let's come back to the core element of the complete paper, not just this proof for the complexity. So the authors state now that the complexity of the language dataset is determined by the information entropy of the text distribution. And the goal is to simplify the language dataset to reduce the randomness of the word occurrences by reducing here the entropy of the text distribution. And this is what is targeted by stating that here the complexity is related to the information entropy. But this is something that I would say, yes, of course. I don't doubt this, no? For the application, now by simplifying in general the language, and they limit here the vocabulary size massively down to 2K, and thereby influence, of course, the word distribution itself. And they remove a lot of outliers, this low frequency word completely. So now they are kind of controlling the distribution of the words in their dataset. And the idea here is, in my words, that the tiny models can learn the distribution properties quicker. Also something I would say, okay, yes. Now for the training. They argue since the tiny LLMs are less powerful, absolutely, they may need to see less complex distribution patterns in the training data itself in order to train effectively. And again, I would say, yes, this is also what I would assume. So the goal was here to provide datasets with less complex distribution. I'm going to show you in a minute how we built this dataset. And I think it makes sense now. If you have an extreme limited AI architecture, from the parameters, from the layers, from the complexity, I think it is self-explanatory that you cannot have highly complex tasks, because those little systems, AI systems with hardly any free parameter, how should they have been pre-trained and imprinted here their tensor structure on a lot of different complex reasoning schemas. It is simply not possible. Or maybe, but then we have to go back and massively change here the backpropagation and find here complete new ways how to do here the feedback loop. Okay. So coming now to the conclusion from the side of the authors, and this is here officially the published conclusion. This is just here my conclusion, if you want, what I saw in this paper. So the official conclusion is that the authors suggested for LLMs and their most widespread application, the agents, the strategy that were tested effectively for the small models. And they have a lot of statistical data in their preprint. So please go there, have a look at it. You'll find a lot of data regarding small models, regarding data set, regarding agents in those simpler language environments. In the authors argue now, they can potentially be adapted now to larger models, to larger data set, and the behavior of agent in more complex environments. Now, you know from mathematics, whenever we deal with an increased complexity, I would not expect here a linear mapping, because we have unknown effects that can take over and take control of this. So this adaptation from the inside of a small model to a medium or a large model, I understand what you do. And I think this work is amazing that they go down to the absolute minimum, 1 million or 14 million free trainable parameter. But if we can adapt the inside, I think, wow, there is a lot of research to be done. Yeah, I wanted to show you they are really transparent. They give you everything. So in Annex G, they give you the prompt for creating now this linear training, linear glue, and linear evaluation data. So you have a background prompt. You just tell the LLM, hey, you're a professional linguist. You got this. So and then you have the general requirement prompt. And then here you have now the simplification prompt. And you tell your, I don't know what you like, your O1 model or your Q1 model. You see, this is the instruction now how to simplify the prompt. And of course, you need training data. So for the wiki simplification, you have here the background prompt, you have here the simplification prompt, and then you have here the examples. Example 1, example 2, and example 3, and you define the output format. So really straightforward. Be careful that you choose here real powerful examples, that you have here really the most significant functionals that you can find here in your system, and then you provide here 1, 2, 3 examples or much more if you have found them. So you see, short video, just wanted to tell you, hey, there are tiny language models. There's a lot of AI research going on, and they have the potential that we can really explore here the behavior of language model to understand new pre-training methodologies, new pre-training data designs that those models need to improve their overall AI performance. So I think this is it for this video. I hope you enjoyed it. I hope I could provide some new insights, some new ideas, and it would be great if you subscribe to see you in my next video.